Hello, welcome to another module in this massive open online course. So, in this module we want to start looking at the KKT conditions or the Karush-Kuhn-Tucker conditions, which are convenient for solving any optimization problem. Alright. So, what we want to start looking at is an important aspect of optimization, also termed as KKT conditions. Also termed as the KKT conditions, and these are the KKT conditions, which are also termed which basically short for the Karush-Kuhn or Kuhn-Tucker. The Karush-Kuhn-Tucker conditions, and these are convenient for solving an optimization problem. So, now consider again the original or the primal optimization problem. Consider the original problem. What we have is, remember, we have minimize G naught of x bar subject to G of x bar equal to 0, I equals 1 to up to m, and G j tilde of x bar equals 0, I am sorry, I equals 1 to up to L, G j tilde x bar equal to 0, j equals 1 to up to m. And in addition, assume that strong duality holds. Let us assume that strong duality holds. Which implies that P star is equal to D star. Now, we know what we mean by strong duality. Strong duality implies that P star, which is the optimal value of the original, that is the primal optimization problem, equals D star, which is the optimal value of the dual optimization problem. Alright, we have the dual cost function of the dual objective function GD lambda bar nu bar maximizes subject to constraint lambda bar is greater than or equal to 0. You get the dual optimal value D star, and if strong duality holds, then P star equals D star. Okay. So, P star is optimal value of primal problem, and D star is basically your optimal value of the dual. Optimal value of the dual optimization. Okay. Now, let x star, now in addition, let x bar star equals primal optimal problem or the primal optimal solution, and that is where the optimal value is achieved for the primal optimization problem, that is x bar is the solution of the primal optimization problem. Similarly, let lambda bar star nu bar star equals the optimal value, and not the optimal value, that is the solution of the dual optimal problem, that is where the dual optimal is achieved. Okay. Then by strong duality, or rather strong duality, so we have, so basically what this means is, that is, if you look at the objective value G naught at x star, that is equal to P star, and if you look at the value of the optimization, the dual objective function at lambda bar star and nu bar star, this will be the dual optimal value, that is D star. That is the optimal value of the dual optimization problem. Alright. So, we have P star and D star, and now from strong duality we have already said this implies P star equals D star, which implies that G naught of x bar star equals the dual function GD of lambda bar star nu bar star. Now G naught, now if you look at this, GD of lambda bar star, now dual function, remember the dual function is the infimum of the Lagrangian. Alright. So, the dual function GD is nothing but the infimum of the Lagrangian over the set of all feasible points x bar. Alright. So, this is basically, or infimum, or basically the minimum. Okay. And this is now the minimum over x bar of G naught x bar plus summation I equal to 1 to L lambda I star Gi of x bar plus summation G equals 1 to M nu j star G j tilde of x bar. Okay. So, G d of lambda bar star nu bar star is nothing but the infimum of the Lagrangian over all x bar at lambda bar star and nu bar star. Okay. So, that is the key argument here, this transition. Okay. Now, once you realize that, the rest of the argument is very simple. Now, if you look at this, this is the minimum over all x bar, which means this is less than or equal to, so remember the optimal value of this is the minimum over all x bar, which means it is less than or equal to its value corresponding to x bar star. Okay. So, this is less than, because x bar star is one particular x bar that belongs to the feasible set. Okay. So, therefore, this is less than or equal to G naught of x bar star plus summation I equals 1 to L, summation I equals 1 to L lambda I star G I of x bar star plus summation G equals 1 to M nu j star G j tilde x bar star, which is less than or equal to G naught. And now, if you look at this quantity, now look at this again, x bar star is the optimal value, belongs to the feasible set, satisfies the constraint, implies this is equal to 0, which implies this is equal to 0. So, this is equal to 0. Now, this again lambda I star, remember, is greater than or equal to 0. Gi x bar star, x bar belongs to feasible set, x bar star belongs to the feasible set. So, this is less than or equal to 0. So, this is less than or equal to 0. So, this is less than or equal to G naught x bar star. And therefore, now you have a very interesting observation. You have started from G naught x bar star, you have ended with G naught x bar star, which are indeed equal. This implies all the intermediate quantities. So, you have the left G naught x bar star less than or equal to right G naught x bar star, which are nothing but one and the same, which means all the intermediate quantities which are sandwiched in between must be also equal to G naught x bar star. Okay. So, which means that all intermediate quantities must equal. This is very simple. For instance, if you have the inequality 5 less than or equal to x less than equal to y less than equal to 5. Now, remember, at the end we have 5 5 and x 5 less than equal to x, x less than equal to 5. There is only one possibility, that is x equals 5, y equals 5. So, all the intermediate quantities. So, similarly, if you follow this chain of arguments towards both ends of G naught x bar star, which means all the intermediate quantities must be G naught x bar star, and therefore, this implies in particular we must have summation I equals 1 to L lambda I star G I x bar star plus G equals 1 to M nu j star G j tilde x bar star. This is equal to G naught x bar star, which implies that now if you cancel these things, G naught x bar star, G naught x bar star, we know this is 0 anyway. So, this implies that the only remaining term, that is summation I equals 1 to L lambda I G I x bar, this is equal to 0. Now, remember, each of these quantities lambda I G I x bar is less than or equal to 0. The sum of several non-positive quantities is equal to 0, which means each of these quantities is equal to, you remember, each of these quantities is less than or equal to 0, but their sum is equal to 0, which means each of these quantities is equal to 0. This implies lambda I into G I x bar equal to 0 for each I, for I equals 1 to up to L. And this is a very interesting property. This is termed as complementary slackness, and I am going to explain this in a moment. This is termed, interesting name, the meaning of this is following. This implies lambda I into J x bar is 0, which implies either, so we have lambda I J x bar equal to 0. So, this implies two things, either lambda I equals 0, correct, which means G I of x bar can be less than 0, or lambda I is greater than 0 and G I of x bar equal to 0. So, in this case, now let us look at this. In this case, the constraint is tight, it is met with equality. And Lagrange multiplier Lm equals slack, okay, that is greater than. Now, in this case, the constraint is slack, gi x bar is less than 0. So, there is some slack, alright, gi x bar is less than 0, which means whatever is gi x bar minus 0, that is the slack. So, the constraint is slack. And the Lm Lagrange multiplier equals tight, because the Lagrange multiplier equals 0. So, this is the meaning of the complementary slackness, that is either the Lagrange multiplier is slack or the constraint is slack. It cannot happen that both the Lagrange multiplier and constraint are slack, that is it cannot happen that lambda I is strictly greater than 0 and gi of x bar is strictly less than 0. This cannot happen, because lambda I into gi of x bar must equal 0. Okay. So, it cannot happen that lambda I is greater than 0, gj or gi of x bar is strictly less than 0. This is not possible, which means either constraint or Lagrange multiplier has to be slack. This is termed as complementary slackness. So, these complement each other. Either Lagrange multiplier or constraint. Okay. This is termed as complementary this property is termed as complementary slackness, and this is a unique aspect of the KKT conditions, that is both cannot be both cannot be, that is it cannot happen that the Lagrange multiplier is strictly greater than 0, the constraint inequality constraint is strictly less than 0. It can happen only that only one of them is slack, alright, the other is 0. So, the Lagrange multiplier is 0, the constraint is slack. As the constraint is 0, the Lagrange multiplier is slack, okay, and this is known as complementary slackness. Only one or the other can be slack, okay, termed only either Lagrange multiplier or constraint can be slack, not has to be slack, can be slack. Only one or other can be slack. Only one or the other can be slack. That is basically your complementary slackness. And the KKT conditions can be finally stated as follows: the Karush-Kuhn-Tucker conditions. These are your Karush-Kuhn-Tucker. And the KKT conditions are basically, if x bar, lambda bar, nu bar are optimal, that is x bar for obviously the primal problem, this is for the primal, and this is for the dual, and strong duality holds. And strong duality holds. This implies that your G naught of x bar equals GD of lambda bar nu bar. Then it must be that then first we have the primal constraints, these must hold. The primal constraints are basically Gi of x bar less than or equal to 0 for I equals 1 to up to L, Gj tilde of x bar equals 0, G equals 1 to up to M. The dual constraints must hold. What are the dual constraints? Remember, lambda bar is component wise greater than or equal to 0, which implies each lambda I is greater than or equal to 0 for I equals 1 to up to L, that is the Lagrange multipliers associated with the inequality constraints are greater than or equal to 0. All right. Complementary slackness, this is the third condition. Complementary slackness, what happens in complementary slackness? We have with respect to the Lagrangian with respect to the gradient with respect to the Lagrangian equals 0. This implies that the gradient of the Lagrangian vanishes, that this implies basically the gradient with respect to x, because remember at x bar this is the infimum of the Lagrangian, correct. At this optimal value x bar we have the infimum of the Lagrangian, which means the gradient we have the minimum of the Lagrangian function. Therefore, the gradient with respect to x bar of the Lagrangian has to vanish at x bar. Okay. Plus, I am sorry, this is not complementary slackness. The complementary slackness, let me just mention the complementary slackness aspect, this will come later. So, the complementary slackness we have already seen that is lambda I into Gi of x bar equals 0, I equals 1 to up to L, that is either lambda equals 0 or Gi x bar equals either lambda I greater than 0 or Gi x bar less than 0, that is either is slack but not both. Either is slack but not both. And finally, since x bar is the infimum, or at x bar you have the minimum of the Lagrangian function, Lagrangian of x bar lambda bar nu bar, the gradient with respect to x bar of the Lagrangian must vanish at this point x bar. That is, we must have delta gradient of with respect to x bar G naught x bar plus summation I equal to 1 to L gradient with respect to I of x bar plus summation g equals 1 to m nu j, the gradient with respect to x of g j tilde x bar, this must be equal to 0, alright. And these are the KKT conditions, and if these are x bar, lambda bar, nu bar are the optimal solutions of the primal and the dual optimization problems, x bar lambda and strong duality holds, x bar lambda bar nu bar must satisfy the KKT conditions. Okay, so these are the 4 KKT conditions that must be satisfied by the solutions x bar of the primal optimization problem and lambda bar nu bar of the dual optimization. All right, so let us stop here and continue in the subsequent modules. Thank you very much.